this video I'm going to talk about the circular orbit because it is the simplest one to explain, because it represents a this is the Earth and this is the Moon. It is the state to which all two-body systems eventually gravitate, because it gives you the lowest level of energy, but it's the most stable. And I'm going to describe the Moon's situation now. It's pretty well circular. We can draw coordinates of space to represent the two dimensions of space occupied by the Moon, R1, and we'll call the other R2. And these are rectangular or Cartesian coordinates, which we can, it doesn't matter where you draw this. It doesn't have to be vertical, but it's customary to do that, as long as the second one is perpendicular to it. A third dimension of space will be coming out this way, and we don't need that because the circular orbit just occupies two dimensions of space. The Moon is traveling at a constant velocity, and the constant kinetic energy added to the constant potential energy represents a total energy which is constant. And this is important because this is the secret of gravity, is that the energy remains constant and the momentum remains constant. And here the momentum is constant too, and there's no problem with this, and this is why it's a simple explanation. The distance between the Earth and the Moon is constant, and this represents, in a non-linear manner, the total potential energy. So I'm going to call this R0. This is the value of the total distance at all times between the Earth and the Moon. And this is related to the displacement in R2, and which is this much, and the displacement in R1, which is this much here, by the following equation: R0 squared, this is the theorem of Pythagoras, equals R1 squared plus R2 squared. And that's one of the things that defines a circle, is that this equation is true at all times. This is the radius, and these are the two coordinates, and a circle is such that this relationship is maintained. Now, this means that if you take the movement in time of the Moon, its movement in R1 is R1. The value of the R1 coordinate is equal to R0 times the cosine of the frequency, which we draw usually with the lowercase omega Greek symbol, times time. And this is with the origin at this point here, so that at time 0 the value of the cosine 0 is 1, so that the value of R1 is the same as R0. And similarly, R2 is the same, except that it's off by 90 degrees, which means that it is a sine, sin, of omega t, the time. And we don't talk about the frequency so much as the period, and W is equal to 1 over the period t, which is what we used in our Pythagoras, in our Newton's equation in the previous video. So that's the relationship, and I'm now going to show the connection between R1 and R2. that they have a relationship with one another that's rather important for, in terms of gravity. If you differentiate these, you get the velocity. So the velocity in the R1 dimension, taking just this up and down movement of the moon, as it goes around, it goes up and down. It follows a curve and a harmonic motion, and the rate of change of the location in R1 with time you get by differentiating that, which gives you R naught. The derivative of cosine is a sine, omega t, and that's the differential of a cosine is a sine, but you have also to differentiate the angle, and this comes to omega, which is 1 over t. So that is and t naught is the period of the whole system. So, and that is equal to the velocity. The radian divided by time is the velocity, and that is equal to v sine omega t, which, as you see, is similar to, proportional to the value of R2. So in other words, the location or coordinate of R2 represents the velocity in R1. And this we're going to use in a later video. But I want to say a few more things about this first. The circular orbit is stable because, remember that we said that R1 equals R naught times the cosine of omega t. R1, if the moon were to stray a little and be pushed by some kind of perturbation, pushed a little further out, what happens? Well, you remember that in the last video I said that Newton's equation for acceleration could be reduced to r over the period squared. And so if in the circular orbit, if the moon were to go a little too far out, in other words, try to go off at a tangent and, by following the centrifugal force, by being pushed by the centrifugal force or by anything else, then this would increase its distance from the Earth, and this would increase the force of gravity, which, remember, this is not generally accepted, but I showed that this is can be the way you can reduce Newton's equation to this in the previous video, and in a circular orbit, that's what happens, and it brings the moon back. And if it were to move in, then this would reduce. The distance between the Earth and the moon would reduce, and the force of gravity would reduce, and it would go back. So it's a stable condition. And you know, we usually follow the inverse square law for gravity, but as I showed in the last video, that applies not to a particular body that's in an orbit like this. There's not an inverse square law. The inverse square law applies to comparison between different systems that are both circular. So if you have, shall we say, Saturn around the Sun, and you have Mars around the Sun, then if you compare the acceleration for Mars as opposed to Saturn, you will find that they follow an inverse square law. By comparing a different system with different energies, the inverse square law applies. But where the energy is constant, if there's a change in the distance, actually there's an increase. And that's why we have this relationship that this equals R1 squared plus R2 squared. Shows you, if you now were to divide this by the period squared and multiply by half the mass, you would get that half the mass times the velocity squared is equal to half the mass times the velocity 1 squared plus half the mass in the velocity 2 squared. And this shows you that the energy increases with the distance for a given period. And this is the reason why we can say that for a system of a constant energy, that if you change the distance, the energy increases as the square of the distance, and the force increases linearly with the distance. And that's something that's not, I think, generally accepted. And you'll be hearing a few more things in future videos that are not generally accepted, but these are my conclusions. So thank you for watching.